Hello and welcome to the 1.05 screencast. I'm Mrs. Willie. This is about scientific notation, SI prefixes, and units. Let's get started. The 1.05 objectives are to use the correct SI unit for mass, volume, density, and length measurements, report the significant, which is the whole numbers at the beginning of scientific notation, to be between 1 and 10, and convert measurements between scientific and ordinary notation. SI units are specific quantities used for measuring. Scientists use the System International, or SI system. Any unit in this system is an SI unit. The meter and other metric units based on the number 10 are one small part of the System International. You use here in the United States measuring spoons and cups, which are not part of the metric system. We also use ounces and gallons instead of liters. And we also use scales. We use pounds instead of mass. The base unit is restart. The base units are units that are measured. So length, mass, time, temperature, and number of particles are the base units. These are all numbers that can be measured. The other units can be derived from them, like you saw in extensive and intensive properties, where my extensive properties are based on measurements, and then my intensive properties are ratios of those properties. It's the same thing here. My base units are based on measurement, and then there are other units that can be derived from those units. So derived means to take from. For our purposes, derived units and scientific concepts are based in calculations using the base units and scientific concepts. Some examples of derived units would be area, meters squared, volume, meters cubed, and kilogram per meter cubed. That means that there's some mathematical operation that has occurred in order to get to that unit. Area is derived from multiplying length, m, times width, m, which is meters, for example. It is also common in North America to use liters to express the volume of a liquid, even though liters are used to express the capacity of a container to hold it. Mass is the amount of matter contained in a sample. Volume is the amount of space a sample occupies. Temperature is a measure of average kinetic energy of the molecules in matter. And density is the ratio of mass to volume. I remember the formula for density using I heart density. From this point forward, we will expect that you have memorized the density formula and know that density is equal to the mass divided by the volume. Conversions you need to know, like you need to have these memorized in your memory banks. The kilo, centi, milli, micro, nano, and pico. The kilo is larger than the base unit. So if I'm talking about a meter, the kilometer is larger than a meter. Centi is smaller than the base unit. So if I'm talking about a centimeter, it is smaller than a meter. So that, as you can see, the exponent here went from a positive number to a negative number because it is smaller. Milli is 3 times smaller than the base. Micro is 6 times smaller. Nano is 9 times smaller. And pico is 12 times smaller than the base. This meter could change. If I was talking about volume, this would be a kiloliter, a centiliter, a milliliter, a microliter, a nanometer, a liter. So that base unit can change, but those prefixes mean the same thing, even if I change my base unit. So kilo, hecta, and deca are all larger than the base unit. Centi, milli, micro, nano, and pico are all smaller than the base unit. Remember again, base units are meters, liters, grams, seconds, Kelvin, or moles. So for example, 1 kilogram is equal to 10 to the third grams, which is 1,000 grams. 1 centiliter is equal to 10 to the minus 2 liters, which is 0.01 grams. So 1 microsecond would be equal to 10 to the minus 6 seconds, and 1 picomole would be equal to 10 to the minus 12 moles. In chemistry, we tend to stay on the smaller end of the prefixes because particles are much smaller, and so there are a lot of them when we're talking about matter. So why do we use scientific notation? To express very large or small numbers in an easy way. This system is also helpful when dealing with significant figures, which we will talk about in our next screencast. The numbers in the significant are always significant. Again, we'll talk about that in the next screencast. In scientific notation, all numbers are expressed as the product of a significand, so that number should be between 1 and 10 and a whole number power of 10. So in my example here, if I were to rewrite this is an ordinary notation, and if I was to rewrite this, I would rewrite it 10.5 times 10 to the 9th power. If I'm going and I have a large number, so if I'm at the decimal and I'm going backwards, that will be a positive exponent. If I'm at the decimal and I'm going to the right, then that would be a negative exponent. When n is a positive integer, the expression 10 to the n means multiply 10 by itself n times. Thus, 10 to the first is equal to 10. 10 squared would equal 10 times 10. 10 cubed would be 10 times 10 times 10, which is equal to 1,000. When n is a negative integer, the expression 10 to the n power means multiply 1/10 by itself n times. Thus, 10 to the minus first is equal to 0.1. 10 to the minus second is equal to 0.1 times 0.1, or 0.01. And 10 to the minus third is equal to 0.1 times 0.1 times 0.1, which is equal to 0.001. Some examples of this would be 2 times 10 to the first power is equal to 2 times 10, which is 20. 2.62 times 10 to the second power, so 10 times itself would equal to 100. 2.62 times 100 is equal to 262. 5.30 times 10 to the minus first is equal to 5.30 times 0.1, which I would move the decimal 1 time over, so that becomes 0.530. 8.1 times 10 to the negative second is equal to 8.1 times 0.01, and I would move the decimal 2 places. In scientific notation, all numbers are expressed as the product of a significand and a whole number power of 10. To express a number in scientific notation, do the following. Rewrite the numerical quantity so that it lies between 1 and 10. Count the places that the decimal point was moved to obtain this number. If the decimal point has to be moved to the left, n is a positive integer. The decimal place has to be moved to the right, n is a negative integer. So 8,162 requires the decimal to be moved 3 places to the left. because this is where a decimal place is if it is not written. So I would move 3 times to the left. This would be ordinary notation. This would be scientific notation. 8.162 times 10 to the third, because I moved to the left 3 times to get the significand between 1 and 10. Here in ordinary notation, 0.054 requires the decimal to be moved 2 places to the right in order for that significand to be between the numbers of 1 and 10. So my answer would be 5.4 times 10 to the minus second, because I moved the decimal place to the right. Before numbers in scientific notation can be added or subtracted, the exponents must be equal. We aren't going to have you do these practice problems, but I thought it would be good to refresh your memories, because now you can just use a calculator to do this. So if I didn't have a calculator, my exponents have to be equal for addition and subtraction. So I would move the decimal place of one of these so that they match. So I just chose to move the 6.0 one place over to the left because I need to make it match the exponent here. And so I have to move it to the left because that's a positive number and it's becoming more positive. So it would be 5.4 times 10 to the third plus 0.60 times 10 to the third. I add the two significants together, and my 10 to the third stays the same because they are equal. So 6.0 times 10 to the third would be my answer. When numbers are multiplied, exponents are added. When numbers are divided, exponents are subtracted. Again, your calculator does this for you, but I just want to refresh your memory. So I would separate the significance from the exponent, the 10 to the exponent, and that becomes 3 times 10 multiplied by 10 to the 4 plus 6, because when I'm multiplying, I add. So this becomes 6 times 10 to the 6th. In division, I subtract. So I would divide my significance and then subtract the exponents. So my answer here would become 1.5 times 10 to the second. And that is all I have for you in this screencast. Thank you for listening.